Greetings, year 13 chemists. Okay, here we've got a rate determining step question which is looking at mechanisms, and history has taught me that students find these questions quite challenging. They're not actually worth a lot of marks, but it is interesting going through the theory behind this, so that's what I'll do to start off, okay? Now, this goes to arrow in chemistry is a bit like opening a book at the beginning, flicking through it and not looking at any of the middle and going straight to the end, okay? Now, that goes to arrow hides all of that good stuff in the middle, okay? Nobody reads a book by opening the first page, skipping all that chunk in the middle and going straight to the end, okay? Nobody does that, but that's what that goes to arrow in chemistry kind of means. But it is hiding, it hides the root of the reaction. And the root of the reaction is what we call the mechanism of how it actually got there, okay? And just a few more examples and analogies. If you've been skiing and you're on the mountaintop, nobody starts right at the top of the mountain and just bombs it all the way down to the bottom. You've got to be quite a interesting person, an interesting character to do that. What you do is you traverse the mountain like this, okay? And you might stop off at a little chalet, have a hot chocolate or some schnapps, right? And then when you get back down to the bottom by traversing through the mountain, you tell somebody, oh, I stopped off there. Oh, I met so-and-so over here, and now I'm right at the end, okay? That's the mechanism. I mean, you could just bomb it straight at the start, go straight to the finish, and that's your goes-to arrow. But this interesting stuff in the middle is the mechanism, okay? So, it's really important in chemistry so we know what the mechanism is talking about. And let's have a look at another analogy. Let's say I am going from London to, I don't know, where am I going? Let's say I'm going to New York. Now, that's the goes to arrow, just saying straight from London to New York. However, let's say for some reason I decide to go from London to Cornwall. Never been to Cornwall, by the way. Heard it's beautiful. So, have to be able to spell it first. So, London to Cornwall, and I decide to cycle. I like cycling. I'm going to cycle that first part of my journey. Okay, so I'm going from London to Cornwall, and I'm cycling. And then, I am going from Cornwall to New York City. But this time, I'm going to speed that leg up. I'm going to go by Concord. If you don't know what Concord is, Google it. So, I don't know if I can spell that, but I'll try. Now that's going to be super quick, okay? This might take 4 hours. So leg B might take 4 hours. But leg A is going to take a substantial amount of time. Let's say it takes me 2 days. So 2 days plus 4 hours is my total journey time, okay? So 2 days plus 4 hours, total journey time. If I speed this leg up, is it going to make a huge amount of difference to my total journey time? Let's say I shave 2 hours off, for example. 2 days and 4 hours versus 2 days and 2 hours, not much difference, okay? However, let's say I speed up the slowest step of my journey, i.e. leg A. Let's say I drive. If I drive that leg, I can definitely take a day off, okay? So if I speed up my slowest step of the journey, well, that's going to have a huge effect on the rate of my journey because I'm saving a day effectively. So speeding up the slowest step of the leg affects the rate. Speeding up the fastest bit doesn't really have an effect on the rate, okay? Not massively. So this is what we call the rate determining step, okay? So that's going to be the RDS, the rate determining step. If I change this leg, it increases my overall rate of my journey. Changing this one doesn't really substantially affect the rate, okay? Now, these are some mechanisms for my journey. What do you notice about Cornwall as well? Cornwall was not included in my overall start and finish because Cornwall was an intermediate stop, okay? So intermediates cancel out when I add up these two legs of my journey, okay? So when we're looking at mechanisms, all steps up to and including the rate determining step must be included as part of our mechanism. So that's just a little theory about what's going on. Now let's answer the question. Okay, let's get these 2 marks. So we're given 3 steps and we have to determine the rate determining step. Now this isn't actually as hard as it seems, okay? So what we're going to do is, before we actually determine the RDS and give a reason, because you're getting 1 mark for the RDS and the 2nd mark for the reason, we're going to write down our rate equation. Our rate equation was, so rate equals K B squared times the concentration of the hydrogen ions, okay? So it's always important to have the rate equation there as well. So if we have a look at step 1, well, step 1 is definitely part of our mechanism because we've got 1 mole of B and 1 mole of the hydrogen ions reacting, okay? Now, let's have a look at step 2. I'm going to draw a line here. What do you notice about BH plus? It's produced in step 1, but it's also consumed in step 2. Well, this is a bit like going to Cornwall. This is our intermediate, okay? And the intermediates do not appear in the rate equation. Bang, bang. Okay, so let's add up step 1 and step 2. If we add up step 1 and step 2, let's see what we get. Are we going to have 2 moles of B reacting? Yes, we are. So that's going to be B squared. Are we going to have 1 mole of the hydrogen ions reacting? Yes, we are. So that's going to be H plus raised to the power of 1, okay? So having a look at step 1 and step 2, are we checking that it's consistent with the rate equation? It is. So, and it's consistent because you've got 2 moles of B effectively reacting with 1 mole of the hydrogen ion concentration. So it's consistent with the rate equation. Okay, so this is the slowest step. This is the rate determining step. And all steps leading up to and including the RDS must be taken into account. Okay, so step 1 and step 2 have to be taken into account here. Okay, so I'm sort of given the reason. The reason is 2 moles of B consumed and 1 mole of H plus ions consumed, so consistent with the rate equation. Now, let's just unpick that a little bit more. If you'd picked step 1 as the RDS, if you just pick step 1 as the RDS as step 1, well, what species would we include? And let's compare it to the actual rate equation. Then our rate equation would be equal to K B raised to the power of 1 hydrogen ions raised to the power of 1. Have a look. Is that consistent with the rate equation? It is not. So RDS cannot be step 1. Okay, that cannot happen. If you'd have picked step 3, okay, let's have a look at what step 3 would be. So if you pick step 3 as the RDS, then we have to include all steps leading up to and including the RDS, so step 1, 2, and 3, okay? Remember, these guys are intermediate, so they cancel out. So what we're saying here is we've got 2 moles of B reacting, 1 mole of the hydrogen ions, and 1 mole of A. So our rate equation, if we'd pick step 3 as the RDS, would be this. B squared, which is consistent. The hydrogen ion concentration raised to the power of 1, but we've also got 1 mole of A. But we know from experiment that A doesn't affect the rate because it doesn't appear in the rate equation. So step 3 is not consistent with our rate equation, so this cannot be. Okay, so it's actually worth doing some wrong ones to see why step 2 was correct. If you're enjoying this content, please subscribe to my channel and click the link in my description to sign up to my course.